to our second speaker, Professor Frédéric Courbin, who is a tenured scientist at EPFL, which is one of the leading research institutions in Switzerland. He has held positions at the University of Barcelona, University of Liège in Belgium, at the Catholic University in Chile, and ICREA, as well as having been a European Southern Observatory PhD Fellow in Belgium and others. He's published over 150 research papers, and he's been part of a number of prestigious research grants, including from the European Research Council Advanced Grant called Cosmic Lens. Professor Courbin has mentored numerous early career researchers who have gone on into promising careers. He has also enabled time-delayed cosmography science, which I explain in part, through programs such as CosmoVerse and TD Cosmo. Frederick, please start in your own time.
Okay, so to complement a bit what was told in the previous talk, so I will remind some of these aspects and expand on other things. So we focus today on things I'm working on directly. So what is called the Hubble tension, in fact, should be the Hubble-Lemaitre tension. And I will tell you what is, of course, the Hubble law, what it means, why there is a tension between what, and why is this interesting at all, what it means for cosmology. I will try to also tell you how the phenomenon of gravitational lensing, that's what was mentioned in the previous talk, deviation of light by mass, can help solving this problem. Okay, so main characters are Hubble and Lemaitre, so I will tell why. So as Laviana was saying, we think we live in an expanding universe. So that means that all the points we know around us at some point were in one single location. It doesn't mean that the universe is a sphere, although that's what's drawn here on that slide. It doesn't mean that we are in the center of the universe. It means that at some point each point of the universe knew of each other and they started to expand. That's the primordial atom hypothesis of Georges Lemaitre, and that was the origin of the Big Bang theory, and then all the developments by Hubble, by Einstein, and all the others. And actually, there are many players in this game. So if we are in such a universe, galaxies are moving away from each other. So you see that galaxies here are all together. Then this one is going away, but it's going away slower than this one that is further away. And then when the universe is expanding more, then the velocity of this one that is far away from that one is higher than this one relative to this one. Now, this is the point of view of this galaxy, but of course you can change the point of view, and you can change, you can go on every galaxy there and you will find the same. And again, the universe is not a sphere and we are not in the center of the universe. The important observation is that when you see a galaxy moving away and you see all the galaxies moving away from you, wherever you sit, it's a strong sign that you're in an expanding universe. So it looks easy now that we know galaxies, but at the time of this theory, in the 20s, so a century ago, we knew nebulae, we knew our Milky Way, and it was the beginning of what we call now extragalactic astrophysics. So the universe is composed of galaxies. These fly away from each other, and in the galaxies there are nebulae. At the time of Hubble, everything was nebulous because it looked nebulous in a telescope, and it was very hard to know the distances, and it's still hard to know distances to astronomical objects. So if you want to measure the velocity and distance to an object, and make the plot that Hubble did, this one, you need to measure, of course, the two axes. The first one, the velocity, is measured with the Doppler shift using spectroscopy. So it's hard, but it's, let's say, still fairly easy to do. And then you need to measure distances. So, in, let's say, kilometers, miles, or parsec, as we do in astrophysics. So that's a different unit. Now, if you do such a plot, you find a line. So that was published by Edwin Hubble in 1929. And curiously, Hubble didn't mention at all the paper, exactly the same paper, but in French 2 years before. With, in fact, all the calculations that Hubble has in his papers, even some of the measurements. So that's why now the Hubble constant, or even the Hubble law, is called the Hubble-Lemaitre law. So what is it aside from the historical configuration? So you have a velocity and you have a distance, and what does it mean, this Hubble constant? So we sit here at distance 0 and at velocity 0. We don't have a velocity with respect to ourselves. And the Hubble law, our Hubble-Lemaitre law, says that the velocity on one axis is proportional to the distance. So in fact, what h0 measures is the expansion rate of the universe now. 0 is the epoch now, that's the starting point. And when you go back in time, you go up to 13.8 billion years. That's the age of the universe, or what we think is the age of the universe. So what this line, what this constant is just the slope of the line. So each time you go up by 1 megaparsec, so 1,000,000 of parsecs, that's this unit we use in astrophysics. It's a lot of kilometers, a lot of miles, not even worth it converting in these units. So each time you go, you do one step of 1 megaparsec, then you increase the velocity of the galaxy by h0 in kilometer per second. And that value is around, we think, between 67 and 74. They look the same, but there is a big difference between these two values. I will come back on this. Also, h0 is, you can see it as a way of estimating, let's say, the radius of the universe. Again, be careful with this. The universe is not a sphere, but it means you can see up to some horizon. That is, in fact, the speed of light times the times it takes to, times the age of the universe. And the age of the universe is given by h0. So h0 is, I was saying, the slope of this line. Here you have kilometer per second and a megaparsec. So h0 is in kilometer per second per megaparsec, which is a very weird unit. In fact, this is a distance, this is a distance, they cancel. So the real unit of h0 is the inverse of a time. Now you multiply this by the speed of light and you obtain a distance, which is in fact some kind of radius of the universe. Or let's say this distance is the time it takes for light to travel the universe during its own age. What is this Hubble constant? So we measure it in the local universe now, so at redshift 0, at age 0. So when we measure distances in the universe and relate distances to velocities are in kilometers per second, but they're also redshifts. Redshift because when you see a galaxy far away, flying away from you, you see it redder, so you see it redshifted. So we measure things in different ways. In time, so today is 0. At the Big Bang, that's 14 billion years ago. That's why it's called look-back time. Now we are at redshift 0, and the cosmic microwave background is at a redshift around 1,100. And then, of course, you measure h0 here in the local universe, but you can measure it as a function of redshift. And that's called the expansion history of the universe. So we measure things here locally. h0 is here. We can measure h at the cosmic microwave background, and then we need to extrapolate it down to redshift 0 using a theoretical model, which is this black curve. Now, what is the problem with the Hubble tension? What is the Hubble tension? No, I said you can measure h0 locally. This will give you this point with these error bars. So that's the 74 I mentioned earlier. You can mention h of redshift 1,000 with the cosmic microwave background. I will show you how to do this. And then with the model, you can know what was the h0 that corresponds to this h of 1,000 that you measured with the cosmic microwave background. So problem is, if you do this, you don't land on this value, you land on this value. And the error bars are sufficiently small that in fact there is a significant difference between these two values. That's what we call the Hubble tension. These 2 points should be the same because they are measured in the same universe. If you measure it directly, locally with Cepheids or supernovae, as Lavinia was mentioning, or if you measure it extrapolated from a model starting from the cosmic microwave background, that should be the same. So problem. What are the possible explanation for this problem? Either the measurement at redshift 1,000 is wrong, or the measurements at redshift 0 here are wrong, or the curve is wrong. And that's, of course, much more interesting, because if you have the correct theory, and let's say this point is the correct measurement, then the curve should go like this. I don't know where exactly, but then it should land on that point. And then you learn that the physics, so the black curve, that is the theory, has to be revised. So that's why knowing if this point is correct or this point is correct is extremely important. Now, how do we measure points here locally? Essentially using what we call standard candles and gravitational lensing. So we'll come back to this. So remember the Hubble law, velocity equal h naught times the distance. You measure velocity using spectroscopy, and the distance, you need a way to do this. So one way is to assume you know some objects that have a given luminosity, a standard luminosity. And then if you see it far away and further away, then it means that it's getting dimmer and dimmer, so you see it further and further away. So that's a generic name for all the standard candles. Cepheids are standard candles. We measure their period, therefore we know their intrinsic luminosity, and then by measuring their apparent luminosity, we know their distance. And for supernovae, the same. They explode always at the same intrinsic luminosity. So if we see them fainter, is that they are far away. And since supernovae are much brighter than Cepheids, we see them even further away. So that's what we call the distance ladder, because we use first Cepheids and then supernovae to build the ladder to see things further and further away. Now, caveat there, you're never sure that your standard candle is very standard. No one tells you that a candle in one galaxy is the same as in the other galaxy. Another effect could be dust. For example, there is a lot of dust in the universe. If there is dust on a line of sight, then you will see your candle dimmer than it should be. So you will think your object is further away than it should be. So there are, I said, there is nothing that cannot be worked around in this method, but it's worth it having other methods. So other methods could be standard ruler. So there the game is the same. You have a ruler, you assume or you think you know the size of the ruler in physical units, so kilometer, parsecs, megaparsecs, and then you measure the angle on the sky of that ruler, and then you do trigonometry and you measure the distance. So the cosmic microwave background is one of these methods. So we'll show you how this can be used. So remember this diagram. You have the local measurement of H naught using Cepheid and supernovae. You have the value extrapolated with a model from the cosmic microwave background, but you need this point here. So how do you measure this point? H of a lot, 1,000. So that redshift is the redshift of the cosmic microwave background. And as you heard in the previous talk, this is the map of the whole sky. The Milky Way would sit here in the middle. It has been removed. So this is a map of the whole sky. And you see here the temperature variation on the sky. Now, according to theory, these dots don't distribute randomly. And that is seen here. That is called the power spectrum of the map. In fact, it's fairly simple. This map tells you, that's an histogram, more or less. It tells you how many points of each temperature are separated by that distance or that angle on the sky. So you see a strong peak here. It means that there are lots of blobs here which are preferentially separated by 1 degree on the plane of the sky. That's twice the apparent size of the moon. So it means that this peak gives you a typical size, typical ruler on the sky. And it gives it to you as an angle. Now, and there I make a big shortcut. Theory tells you that there is a physical value for this corresponding to this angle, and therefore you can use this as a standard ruler. So you measure, in fact, the distance to the cosmic microwave background. So you have a distance here, you have distance to fairly nearby objects, and then you have theory connecting the two, and the things don't connect. So this is the origin of the Hubble tension. So what we want is really to make sure that this point is actually here. Maybe it's wrong, it should be here. Maybe there are assumptions in the CMB that are wrong, and in the end, this point is not correct. It looks like it's not the case. There are more and more clues that this tension exists because this point is correct, this point is correct, and the hope, because that's the more interesting thing, is that the curve is not correct, that the standard model, cosmological model, is not at least completely correct. Okay, so there is another way to measure distances. So I told you, standard candles are essentially a ladder. So yeah, there are many interconnected steps, and now it would be nice to have another method that is, for example, a single step method, and that is not affected by dust or the universality of standard candles to measure distances. And lensing is one of these methods. So you have here a schematic example of what happens. You have the Hubble Space Telescope, a galaxy, which is a lens, and this is what we call a quasar. So that's the bright nucleus of a galaxy, super far away, well aligned with the lens. And then the light will be bent by this lens, which is why we call this a gravitational lens. So mass will bend the light just as an optical piece of glass. And then what we would see of the quasar is not one, but several images of it. So four in this case. This is a real image of a gravitational lens. And this is a number of other objects that we have been playing a lot with in the TD Cosmo collaboration. We have 7 for now, but we have observed about 50. So there will be more developments using this method. But how the method works. So I told you have an observer, a lens, a quasar, and then you have the light that is bent, and then you have, in this case, 2 images of the quasar, and what you see on the plane of the sky is the lens, and behind, through the galaxy, you see the quasar. So now what happens if the quasar emits light? So you see the light propagates along 2 different paths that have different length. So photons don't arrive at the same time at the observer. There is a time delay between the arrival time of photons from one image and the other, or the others, if there are many. And this is related to a ratio of these 3 distances and to h naught. So the time delay, if you can measure it, this is the one. I will show you how. Has 2 origins, a geometric origin, because the optical path to the lensed images of the quasar are different in length. And the photons go through the potential well, so through the gravity, let's say the gravitational field of the lensing galaxy, and it does that at different places with respect to the center of the lens for each image of the quasar. And that creates an extra gravitational delay. So if you can model this very well, and that's hard, but it's feasible, and if you can measure this, you can measure the Hubble constant. So the idea is not new. It was invented in 1965. It's only now that the method is actually feasible observationally. And if I summarize it, essentially, you remember h naught has to do with the size of the universe. So if you live in a big universe, then h naught is small, because the radius of the universe is proportional to the inverse of h naught. Then you get a big universe, small h naught, large delay. If you could shrink the universe, then your h naught would be larger, and then the time delay would be smaller. So essentially, you want to measure the delay, model the lensing galaxy, especially to model the gravitational part of the delay, and then what you get is the method that gets you h naught in a not simple way, but in a single step. There is no ladder there, and the time delay also does not depend, on dust along the line of sight. It doesn't depend on if your quasar is a standard candle or not. So I'm not saying this is any better than other method, but it's completely complementary. Which is why I show this specific method here. So it's a good cross-check of other methods. Now, to do this, you need the time delays. I will show you how to do this. You need very nice images of your object. This is the lens, and you have here 1, 2, 3, 4 times the image of a quasar in the background. And as I was saying, what you need is to model very well the mass of the lens. So this thing, including the dark matter, that's the difficulty, because of course you don't see it. So you have to, it's a free parameter in your models. You have to make assumptions, and you have to estimate if these assumptions are right or not. So in fact, a lot of the effort currently is on this aspect of the work. And on top of this, you need to know how much of all the galaxies along the line of sight, this one, this one, this one, have mass that leak, let's say, that affect the potential well of the main lensing galaxy. And you have to do a correction for this. So if you can do these 3 steps, you can measure the Hubble parameter, so H0. So extremely important, the time delay itself. So I told you the objects have to be variable to see that, and the objects are not varying fast in the universe. These are years. We started this program in 2004, finished around 2020, and we followed the photometric variations of the quasar images. So, in one image, you will see the variations of one image, of course. Remember that this is 4 images of the same quasar. So what you would see is the same variations shifted in time by the time delay, if you measure what we call the light curves of the quasar images. So that's what we did here. That's 1 point every few days for 20 years, essentially. And we measure very well this shift in time. Now, you should, in this specific object, these 3 objects, these 3 images almost don't have a delay, but there is a longer delay between this and the other 3. So the purple curve is this one, and the other 3 are these ones. So if you can probably catch some features, like for example, this one in the purple is in fact this one in the other ones. So the shift is around 100 days to give you orders of magnitude. So you have to measure this over a very long time. There are other reasons for doing so long monitoring, but I will skip the details here. So that's the main ingredient. You get the time delay, you do the modeling, you estimate how much mass of all the galaxies along the line of sight contribute to the deflection of light, and modify the potential well of the main galaxy, and you get H0. So you do this for many lenses. We have 7 for now, and this is the typical values we get. So these curves are what we call the probability distribution functions for H0 for each of the lensing objects. And that's for, let's say, the combination of all the lenses. So we obtain a fairly high value of H0 compared to the 67. So that tends to confirm the low redshift point. So Cepheid, supernovae, and now lensing tend to agree on this point. So the tension seems to be really real between this value and the extrapolated value from the cosmic microwave background. And to conclude, okay, so is the tension real or not? So do we really have discrepant values of H0 at low redshift? My answer is probably yes, but we need to make really sure that the error bars are correctly estimated. And one way of doing this is using gravitational lensing, because it's not a ladder. So yeah, there are many, the method has its own drawbacks, as you have seen. You have to model very well the lensing galaxy, but it's completely independent of any other method. And also reassuring is the fact that all lenses are very different to model, and still they give the same answer, high value of H0. So method is independent of the others. And also a very nice thing, it depends on really well-known physics. It's only gravity. There is no complicated gas physics or magnetic fields somewhere, or dust, or or stellar physics even. We don't know if Cepheid stars, for example, are actually standard candles, or are there sufficiently good standard candles. All this to say that in the end we support with lensing the high value of the Hubble constant. So Hubble Lemaitre, I should say. So thanks for your attention.
Thanks so much. Thanks for a really nice presentation, and also thank you both speakers again. So to the schools, first of all, just to mention, I would just like to highlight some teaching material we've prepared as part of our post-action network. And now it would be nice to go to the question and answer session.
There is one question. The person wants to know about black holes. Yes, black holes are really cool objects, one of the most fascinating astrophysical objects. In fact, general relativity, so the theory of gravity, predicts these black holes. So when you take Einstein's theory and you solve it for certain conditions, you get these black hole solutions. And the black hole is a region where gravity is so strong that not even light can escape it. And so we have no means by observing it and getting light of the black hole. Therefore it's black, so it's completely dark. And now we are even able to measure the ways how black holes interact with each other. So if you have, for example, two black holes and they rotate around each other, and at some point, if they come sufficiently close to each other, they merge together and give rise to gravitational waves, which we are then able to observe. So probably we could do another seminar on black holes, but this would be a short answer.
Maybe if I can add, because there are lots of things where black holes can occur, and you have stellar mass black holes. So some stars, some very massive stars collapse to a supernova, and that results in a black hole. That's a few solar masses, not much. But the centers of galaxies also have what we call supermassive black holes. And it's not really clear if because of the black hole you form the galaxy or the opposite. But these things, like in the Milky Way, can be like millions of solar masses. And we even have an image, not of the black hole, but the region immediately next to the black hole in our own Milky Way. So we start to see a black hole or see the effects of black hole directly. So they are not purely theoretical objects. And maybe another important thing is that while this is an impressive phenomenon, black holes are super powerful, super compact, they remain rare, and in fact, in mass, they are not much in the universe.
Excellent. So I think Pieros has a question.
Yes, thank you. We have a question from International Bilingual School of Provence. The question is, if all the galaxies are moving away from us, do you think that it would be possible to explore all of them?
To explore them physically, go there? No, certainly not. But we see most of them with telescopes. Yes. Actually, there is a satellite now flying, Euclid. So it's a European mission that maps that is doing a map of the whole universe, the whole visible universe, in the optical and in the infrared. And there are also other experiments doing spectra, so we can measure velocities for millions, if not hundreds of millions of galaxies now.
So maybe to emphasize, so within the universe, there is only a region of the universe where light has enough time to move from there and reach us. And there's like a horizon around us from where we can observe all the galaxies because they are sending their light to us. But at some point, if they are outside and the light doesn't have enough time to propagate to us, then of course we cannot observe those objects. So therefore we can, for example, not answer whether the universe is infinite or finite. We can only tell something about the visible universe where light has the chance to propagate and reach us.
There's a question in the chat.
The question is about whether or not we can actually tell something about the past of the Earth by observing the stars from long ago. So unfortunately, we are attached to Earth, right? So we cannot simply move away quite some distance and then observe it from there. But we can observe is all the stars around us and their typical observation. And if we now also see that a given star has planets, which are maybe very similar to Earth, then we could try to, make basically suggestions which kind of evolution or this planet formation that Earth might have gone through. But no, the answer to this question would be a big no. No, we cannot see the past of Earth directly off Earth, but instead what we do is we take probes of Earth going down and from the materials of the Earth, and we do chemical analysis and then try to see the decomposition, and from there we try to see what type of evolution Earth has gone, but we cannot do that from space.
Now there's a classic question about whether the universe is infinite, so a more standard question.
Yes, I think I had already answered that question when I was talking about that we can only see the horizon around us and where the light has the chance to propagate to us. Therefore, we cannot answer the question whether the universe is infinite. We can only speculate about it, but we don't know.
But it's not in contradiction with expanding.
Of course, one tends to have this image that it expands, so it must be expanding into something.
Yeah.
But it's this space-time together, right, that it's expanding, and you have to visualize it in a way that it's not something that is expanding into something. It doesn't mean that you should have higher dimensions in which this four-dimensional space-time is expanding. So you have to somehow distance yourself from this type of visualization.
Any other comments, questions?
So if the universe is expanding, then what is it expanding into? What is beyond the edge of the universe?
Well, it's a bit, what was said just now, that the universe doesn't, can expand, doesn't need to expand into something. And since, we also have a limited view of the universe, we can't say what's beyond the part of the universe that is accessible to us, thanks to light. So there is no clear answer to that. Yeah.
Thank you.
There's one more question from international school. Is there life on another planet?
Can do some kind of a posteriori statistics. We exist, so there is life on at least one planet. And the first exoplanet was found in 1995, and before that it was not. Although people were saying, oh, it's very likely that stars have planets, there was no proof. Now it turns out that half of the stars we know have planets. Now you can also think that we are in a galaxy that has a few hundreds of billions of stars. Half of those have planets. So that's a lot of planets, and there are billions of galaxies. So billions of planets, so it's very likely that life is somewhere else. If there are UFOs coming and visit us, that's another story, because probably not, because the trip is too complicated to organize, let's say. Now distances are really too far. If you even in our galaxy, if you take the sun as an orange, the nearest star is 3,000 kilometers away. And it takes you 4 years at the speed of light to visit.
Maybe here would be a good time again to thank both speakers. So thank you very much for really interesting, insightful presentations, and also to the students and the educators for making sure, joining us in this time. So thanks everybody.